Hi, welcome to our video solving analysis of structure using STAAD Pro version 8i. So actually there are a lot of versions and we can use whatever available. And in this case, in this problem, we're going to solve a plane truss structure. Given that all members are double angles, this property short legs back to back, its area is 4.97, so on and so forth, and we have these values for its properties. And here we have our structure, and we are tasked to determine the reactions at E, vertical and horizontal, the axial forces in bar AE, and so on and so forth. So in our last video, and previous we had solved structural analysis of a problem that is a beam, still using the same software. So let's proceed with our structural analysis for the this plane truss problem example. So here we have our menu for the STAAD Pro, and in this case we're going to create a model that is a truss model, and we're gonna name this P plane truss. Then the same file directory, and with the unit that is kilopound, and a foot is in metric. So next, we click next, and then we add a beam and finish. Then again we proceed with the command window, and in this case there's actually a program. There is actually a ready-made program. It's a structural wizard that that allows you, or actually allows me to input the parameters for the truss that is already given, the bay, the height, the number, the length, the total length, so on and so forth. So let's try that and directly make a truss model, and then just some few edits, and we're done. So as you can see from our given, it's actually a Howe truss. So I'm gonna check Howe truss bridge, and the total is actually 60, and height is actually 20 feet. Width, since it is not specified, so I'm gonna put 0 for the base along the width, and the number of base along length, that is 4. And we're going to check this 15, supposed to be 15, so that is what is emphasized in our given problem. Then we'll check, then yes. And if we go back to our structural wizard, the command prompt, we can see that it appears a structure, given structure. However, it's somewhat still different from our given, so I'm just going to perform edits now. So I'm going to remove this beam, delete this beam, and then along with this node, node selection, then delete, and the beam will be deleted along with it. So I'm gonna add some I'm gonna add new beam to this part. That's it. We have our structure. Let me test, or actually try if our dimensions are correct. So I'm gonna scale. Display. So our display are this. So here we can see that the display according to our given is actually correct. So 15, 30, 15 feet, and our height is 20 feet, with corresponding values for the diagonals. So to avoid subtlety in doing and adding properties and etc. and proceeding with the structure, let me remove the dimensions. Dimensions and then remove excuse. Okay, now we will proceed with adding the support. So again, same process, create a support, but from our given we have to see that the support that is present in our structure is a pin in the roller support. So just have to add a pin support, add, and then add a roller support. Same process from the first video, that is to uncheck or to not include checking the FY, then add, and then we go with applying the load. I mean, not the load, the support, but the node, the specific node, that is node D, node 1. So assign, and then click yes, then support 3, then highlight the load, then assign, then click yes, and there we have created our supports. And after that, we are going to define the properties of the material, not the property and the material of the structure. So we'll go with defining it in the section database. It's kind of loading, so it will take a while. Maybe it's because of my laptop is not being high end. So in our given here, let's proceed with defining the property, the material property. So take note that all the members are double angles, 4 by 3 by 3 by 3 by 3 by 3 over 8, short legs back to back. So in our software, I actually run using the section database because it will present us actually all the type of materials that we can have as an option or as given that we have to select. So since it's a double angle, so I'm gonna click the angle, and then I'm gonna view the table to look for this given material or dimension, and then look for its code, because the code is using its TAD name. So it's actually L34 over 38. Here we saw it. That's L4 by 3 by 3 over 8. So it's L4 by 3 over 8, and its code is L40-306. So we close this. L40-306. L40-306 here. So it's actually a double angle short legs back to back. So we're gonna click the short legs back to back, then click the code for the L4 by 3 by 3 over 8, and then yes, it's a steel, and then click add, and then we can see that the material is already added. It's actually this L40-306 is actually a section code for the L4 by 3 by 3 over 8. Then close. And then this is only the materials that we require, because it is applied to every members. All members are actually in this type of material. And then we assign, because we already have highlighted all the, and so we just have to assign. Let me edit the dimensions, because these are so big. How am I supposed to? Here. Dimensions. labels, commands, labels, I totally forgot where to edit delay. Okay. No, it's not this. I'm talking about the you just have you just don't mind about this. Regardless, if you're going to tap geometry and etc., it will be gone. So now we have already assigned the material, the properties, and etc. for the members of the structure. Then we proceed with applying the loads. So go with to the loads and definition. Add load case detail, load case actually none, load case 1 by default, close, and then add a load case. So it's actually a nodal load. So first we're going to apply the 1.2 kips at this node E in our structure at this point. So wait, for further visualization, let me actually view the nodes, beam labels, font, the size, just 10 or 11, okay, and so node labels, font, 10 will do. Then click apply and then okay. Labels, number, unknown numbers, members, beam numbers, then apply and click it. Okay, so from here we can see the beam numbers and the beam node, the nodal numbers. So it will help us for easy and casual, direct tracking. So it will guide us further and it will make the work easier. So at this point, we are going to add or apply a load. So these loads 1.2 kips and 1.5 kips. You can see here the corresponding nodal number of node E from our structure. The model is actually here in our software is node 2. So we just add load, then nodal load that is along the y-axis. So since it's going towards negative 1.2 kips, add, and we can see that it's already added. Now we add the 1.5 kips, add, and then say 0, and then from at node C, that's actually node 8 in our structure. It's along the x-axis, that is still going to the right, so that means negative. So negative 2 is negative 2 kips. Then close, add, and then we close. Now what we have to do now is to assign these loads to the nodes to which or to where it is actually applied. So Fy actually applied at node 2, which corresponds to the node E at our model structure. So our reference model structure. So 1.2, so I'm gonna highlight it there and then assign. So it's already assigned, and then just gonna have it here and then apply at node 4 corresponding node. Assign. It actually didn't work for this part. Assign, then click. Already have it there, and then for this, from our reference model, this at node C that corresponds to node 8 in our software structure. And then we just have to click this, then this, and there we have applied all our applied loads. So now what we have to do is to perform an analysis print, print and add, so that we can run an structural analysis. Then it goes, and then we just have to highlight this whole structure, and let me visualize to you the rendered view. This is actually the rendered view. So this is what a double angle L4 by 3 over 8 looks like. This is what it looks like. That's how it looks like. Amazing, right? So let's proceed to our analysis. Exit this, and then let's analyze the run analysis. Hopefully there will be no errors, so that we can determine already all those required. Yes, there are no errors. Then we go to the post-processing mode, then done, and then we just have to double tap this load case, okay, and then there. And the first thing that we have to identify is excuse me, the reactions at D. So that corresponds to our node 1. Reactions at D. Reactions D, we just have to tap the reactions, then load case, then okay. So we will obtain our reactions. So reactions, we have the vertical and the horizontal reactions. So let's go first with the horizontal. Let's do keeps. So we just have to input 2.00 keeps. And for the vertical one, that is 1.942. 1.942. And then the actual force in bar AE. Now in determining the actual force in bar AE, I just have to tap this. This is the actual force, our actual force, and then we just have to view the table. So this is actually the diagram for the actual force. So as you can see, it's not really visible. It actually blends with the original structure. So it is mainly because of how big the structure is with respect to its length. And provided that, and given that I don't know yet how to edit the visualization of the diagram to show it more presentable and more recognizable to me, or to the user, to me as a user. So I'm just gonna go and proceed with the table, and then I'm gonna just view the analysis for the beam and the beam forces details. So I'm just gonna view the analysis result and click OK, and then it will provide me the actual forces. And from here the actual forces required to be determined is bar AE. That actually corresponds to number 7 in our software. So we just have to locate the number 7 from here, and that is our maximum. We're talking about the actual force in bar AE. Tips. The actual force in bar AE. That is negative 1.942. So that's our value. Negative 9.142. 942. The 1.942. Just have to input it here, negative 1.942. And for our BE, that actually corresponds with our member 12. So basically that is just have to locate and then obtain the actual force. Number 12 is actually 9.97. It is positive 0.97. Positive 0.927. 0.927. That's it. And so we have obtained the actual force in bar A. Now proceed with the nodal displacements at C. So at C is actually at this point. So the horizontal and vertical displacement for the nodal displacement. So we just have to exit this since we already have obtained what we wanted, what we have to obtain from there. We just go with the displacement, and then we will obtain the nodal displacements at node 8, not a corresponding node of nodes from our reference model to our model in the software. So node 8, our deflection, the displacements along the horizontal is actually negative 0.07. So we just have to input here. See, that's 8, node 8, 0.007, negative 0.007 inches. Actually, inch and negative 0.008 in horizontal, x vertical, y. Okay. 0.008. Okay, so that's how we use the STAAD Pro in analyzing this plane thrust structure. And yeah, I hope you enjoyed watching this video and I hope you learned something. Thank you. Please wait for the other video following this, solving another structure. This is our structure at sea. So bye.